Now, I know that wasn't a lot of time, and some of you were like, oh, I didn't get to finish my cool, be friends and talk to nutrition. Go team. Okay, so here we go. Ready? We are in section 1.4. We're on day 2. We're not done yet, though. That's going to be tomorrow, which is why the homework's not due until Thursday. Here's the big thing that I want us to get down, hopefully by the end of today. I'm not totally sure if we'll totally get through it. Biggest things, actually I'll put 2. One of them is translating into math. Translating into math, what's that all about? And the second huge thing from today is domain. You see, Honors Precalc was working on domain a little bit more, so domain might have to continue tomorrow also. But 2 big things from today. Translating into math. You guys see it up here, translating into algebraic. Translating into math, and then domain. Those are 2 huge things for the rest of the year that is going to happen in this section. And this section's big, because we already had stuff yesterday with data that we were talking about. Like, we're going to be given stuff. This is what the example was that we didn't really officially do. I just talked about it quickly. We thought about the different ways we're going to get data. As, hey, verbally, sometimes they'll give us like actual paragraphs that we have to kind of figure out what's going on and how do I mathematically represent it or mathematically think about it. That's the verbally. How is this information being given to you guys? Out of the 4? Yeah, numerically, the tables and the data points. This could also be given to you even in like a paragraph, and they have like different ordered pairs or different data that's being listed. There are statistical studies and polls that are done. Go take stats. You'll learn more about all of that. Practical, collecting all sorts of data and trying to make decisions and predictions and all sorts of things based on it. Graphically, given graphs, that would be the last one, right? It's kind of numerically because it's points, but at the same time, it's given in a graph for you to visualize. And then even though I said this is probably the last one you were introduced to, I think you saw tables before you saw equations. You saw, well, definitely you learned words before you learned equations, right? Just in general. Graphs and equations probably came about the same time. Almost everyone says this is the easiest, but there are tricks. There's familiarity that you have to be able to get with equations. There are so many mistakes that can happen when you're doing math to equations. So even though it might seem like the easiest one out of the 4, I mean, some of you might like just words better, like, give me a paragraph every day. Like, ugh, equations, no thank you. Depends on your brain. But most of us are going to end up liking equations more, just there are so many mistakes that can happen. So we saw the rule of 4, how we're going to get data. We talked about functions. So yesterday was important, but today there's a lot more going on. So let me go ahead and make this as big as I can. You guys already started writing down, I think, these notes. And if you're wondering, why are we writing down about translating? Well, it's because of this problem on the next page. That's a doozy. He's a bit intense. There's a lot going on. Especially if English isn't your first language, you're like, that's bad. Okay? Let's talk about at least some of the words. Because right now, if you're reading this fast, you're like, can and for. I don't know what to do. Right? Like, can and for, I'm done. So before we get to this page, let's at least talk about this really important, or these really important words and what they actually mean and what they lead us to. Why do you guys think it's important to talk about translating in math class? When do you usually talk about translating? Huh? Oh, well, graphs. Okay, that's true. In Algebra 2, translating a graph, shift it right, left, up, down. But I mean translating as in translation, as in what non-math class has to deal with translation? Spanish, French, maybe English a little bit, right? Right? Translating between languages. So is math a language? Kinda. You're going from words to numbers, to variables, to ways of setting up equations, to... Why? Because this is hard, right? And it's a lot easier. Instead of saying the ratio of the height to the radius is 4, quick example, it's a lot easier to say, oh, you mean h over r is just 4? What would your brain rather do? Have to worry about all these words or get to this fraction? Most of us would say, give me this every day. Like, I don't really care about that. I just care about, I think I need this to do what I'm supposed to do. So that's kind of what I mean. Translating makes the words a lot easier if we can take them and summarize them. And wait a minute. Have any of you guys read the comments on, oh wait, I was finishing honors last night, wasn't I? When you're writing your directions and your problems in your homeworks, when you're writing your directions and your problems in your homeworks, isn't it just faster to take the words and either shorten them, right, summarize them, and say something about making a soft drink can narrower, taller. Like, okay, some of it's just like shortening the words and trying to understand the main idea of the first humongous, that's a new word, you're welcome, humongous sentence. But then also, you don't have to write all these words down if you can just tell me what it means. So it even makes your job easier when you're trying to summarize directions and problems. Does that make sense? Okay, so there's a lot of reasons. Some of them are selfish, but it's okay. It's not a bad thing if you're trying to simplify what's going on. But translating into algebraic notation, if I'm saying y is a function of x, or y is a function in terms of x, I want you guys to go ahead and box the function of, okay? And then box the function in terms of. I also want you to come down here and box depends on. These are 3 different ways, and they're not the only 3 ways. I wish they were, but they're the main 3 ways. That a word problem can tell you who is y and who is x. Because here's the sad thing. Remember calculator worksheet number 2? I think I have an example right over here. Calculator worksheet number 2. Okay. You guys were dealing with years and populations, with times and with heights, with, oh, they didn't even tell you what that thing was, X's and Y's, with age, how old like female babies were, months, and then pounds. Speed, miles per hour, and stopping distance, feet. Nowhere in this entire worksheet, which was full of all sorts of different data that you had to analyze and work with, nowhere did they say, hey, by the way, X needs to be, Y needs to be. They didn't say it once. Now, as a class, do you remember that we talked about who was X and who was Y? We tried to like help you relate the two. But it's super hard if you have a word problem. They just say, hey, by the way, here's 2 quantities. Because remember, a function and a relation just takes 2 variables, 2 quantities. Does it have to be X and Y? No. But what are we used to? What are we most used to? Equations with X and Y, right? So then we have to figure out, okay, if they give us a huge word problem, if we ever see the terms function of, or function in terms of, or even just in terms of, or depends on, whatever thing comes before, whatever variable comes before the wording will always be the Y. You can always make that the Y. And whatever comes after, you can and you should and you need to always make the X. Now in calculator worksheet number 2, I think we were mostly given tables of data. So they weren't really like explaining the whole situation going on. But in this page over here, they're totally explaining what's going on. You're working in the marketing of a soft drink company, yay, and experimenting with a new can for iced tea. Slightly narrower and taller. They're trying to tell you the situation. They're telling you down here about height and radius, H and R. Height of the can, radius of the can, remember only half the distance from the middle out. But then letter A, okay? In your notes, are you summarizing the example, practicing what we do in homework? Have you gotten here yet? You should probably start. So what you should do when you come to a homework problem like this, take the whole paragraph, read it through once, as I just did, and then say, how do I get the important stuff down? New iced tea can. I think you can almost summarize the whole thing. New iced tea can, narrower, taller. H over R is 4. Done. There's the whole paragraph. New iced tea can, narrower, taller. H over R is 4. That's the problem. kind of like the directions because it's the stuff you need before you even do the problem. Letter A. Letter A. What variable are we going to use for volume? What do you think? Volume of a can. Well, radius is up here. Good. But what are we going to use for volume? Good. Volume is a measurement. Area is a measurement. Surface area is a measurement. What variable are we going to use for volume? There we go. Okay, so couldn't we take all this and say V is a function of R? We can say that, right? V is a function of R. That's the directions for A. Directions for B, what would you guys say?
V is a function.
Good. V, function of H. So using the translating techniques, guys, who's going to be your Y variable? Yeah. Yeah, Y is going to be V, right? Who's going to be your X? Yeah. Has to be that way. There's no other way to do it. So V is going to be a function of R. V is going to be a function of H. I know that V's are my Y's. And wait a minute, when we make an equation, don't we almost always do Y equals? So we're going to do V equals on both of these. Now we're going to get back to, in just a second, wait a minute. They didn't tell me what V equaled. They didn't give me that equation. It's not even in words. Geometry, volumes of solids, I should know. But pause over here real quick so that we can move on to the example and zoom in on it. Who's the independent and who's the dependent? Do you guys remember?
Volume is the dependent.
Oh, I apologize, Joe. Hold on. Not that example. Coming back to Y's and X's. Who's normally the independent? X. Good. If you want to think about it, do you remember in calculator worksheet number 2, the X was almost always time? What's time just keep doing? Yeah, you can start singing a song if you want, but time just keeps going, right? Into the future. So time just keeps going, right? It's independent. It doesn't matter how hot, how cold, how this, how that. I think one of the studies was babies and how much they weighed. It doesn't matter if they weighed a little or a lot. It doesn't matter. They're going to keep on growing older, right? Time just keeps going. So time, he's always the X guy. That's our independent variable. And then the dependent variable is the other one. Depends on, that's the Y. I mean, this one kind of helps, right? Y depends on, so he's the dependent one. X must be the independent one. Okay, all that. Let's zoom in on the example. Has anybody taken just a moment to think about geometry and solids and area volumes, etc., that you were supposed to have memorized way back when? Remember that we had a cylinder? Remember a formula that went with cylinder and volume? Nice. Now, how do you remember that? How could you have remembered that? Volume works with, at least geometric solids, excluding spheres. They're weird. Area of the base, if something does have a base, times the height. Well, what's the area of a circle? And then you have to the technical term is accumulate it. Accumulate it through the height. Pi r squared times height. Yeah. So that's, okay. They didn't tell us that. Here's the sad thing. They expected us to be able to kind of, not pull it out of our butts, but at least remember it, sort of. Wait, well, that's mean. So we're going to have to remember all sorts of geometry stuff? Has anybody noticed? There's some cool referencey thingamabobs in the back with areas and volumes and different solids and all that jazz, okay? So if worst comes to worst, you could have looked back there. I know some of you don't like that. You're like, they should have given me everything I needed. Well, they're expecting you to become a little more independent as you go higher in math. Like, they're not going to always give you what Pythagorean theorem is. They'll expect you to be able to remember and use it. Does that make sense? Sort of. So we're going to take Joe's formula, pi r squared h. Why is that formula not good enough the way it is to plug in right now for the answer to A? A says only R and B says only H, but what's the dilemma of this whole formula? I want you in your groups really quickly to talk about the dilemma. The formula has R's, has H's, Is there any way to get rid of the h's and get r's, or get rid of the r's and get h's? Ready, set, go. Talk. And if everybody agrees, try to do it. If everybody agrees, try to do it. If everybody agrees, try to do it. How do you just get r's? I heard some stuff and then it got really quiet. I think a couple people started trying and the rest of you guys just were like, oh, I don't know. Someone who thinks they have an idea and they're trying something, what are you looking at besides the volume formula? The h over r equals. Can we use that? It's supposed to be true, right? Who don't you want if you only want r's in the formula? What do we do if we don't want something in math? You substitute. But you can't substitute until you get it by itself. Oh, so let's get it by itself. How can we rewrite this guy? Can't we say something like h equals 4r? Or for this one, can't we say that r equals times r divided by 4? Check it. Play around with the equation, but we can get r by itself. We can get h by itself. As soon as we get it by itself, can't we plug it in to wherever it needs to go? Substitution. So for this one, we multiply r on both sides. For this one, well, 2 steps. We had to multiply the r and then divide the 4. You can see it here, I think. Divide the 4 and you get r by itself. So now, aren't we good with, wait a minute, we need to plug in. We think about parentheses anytime we have variables. Right around the variable, that's how we plug in. So the first time we're plugging in for h, right? To get pi r squared times 4r. What would that simplify to be? 4 pi r cubed. Because if you want to think about it, for those of you that are like, wait, what's going on? This is multiplication, right? Values next to parentheses. And there's no addition or subtraction, so no distribution is going on. This is just simple, like, multiplying. R squared times r. R cubed. We always put 4. We have volume as a function of r and r alone. Check. Done. But there was a lot going into getting there, right? So what are we going to do for letter B? Replace the r this time with what we already figured out he is, which is h over 4. Which simplifying is harder? What do you guys think? A or B? Yeah, B is definitely, because you have a fraction, he's being squared, right? He's a fraction, he's being squared, but you guys know how to square fractions, right? Can't you just think of h over 4 times h over 4? Ready, set, simple. We're super independent. Stare at me. Sleep, and then it's a struggle. The door's open. The air should turn on soon. I have a way of kind of tricking the system. Hang in there. I know it's hot in here. Hold on. The cold air should be coming. But for right now, make your brain work. How would you simplify? If you hate fractions, start putting things over 1. And then multiply across. If you need it. You should end up with, yeah, except one thing I'm going to change, Joe. The pi is technically a number. So since it's a number, give it like a coefficient that always needs to get written in front. Okay? So hence why it's pi h cubed, not cubed pi. Not that you were wrong, you were correct, but the notation was a little bit off. So a quick reminder of a property too of fractions, that when you square a fraction, you square the top and the bottom, or it's h over 4 times h over 4, which is h squared over 16. What made this problem hard from the very beginning? Okay, words, right? What made it hard after you even figured out what the words were saying? Yeah, the whole, okay, we have V's and R's and H's and we're supposed to, and we didn't even have this, right? So first it was the words, just figuring out what was going on. Second, it was translating what they wanted. Third, it was, well, who's even volume? And fourth, it was like, oh, stink, we have this little hidden clue and he's the key to everything to making it possible. Was it a hard problem? Yes. Is it impossible? No. But where does it start? Turning the words into math and reading the questions and figuring out what they want. And all of that comes back to translating. Bless you, bless you. Okay, translating. Did we work on it? Yes. Did we make it easy? No. But hopefully easier. See what you can do in homework. Don't give up on me. Okay? Okay. Word problems, and it might be towards the end of homework. You might be doing it till tomorrow night if you're not able to get through the beginning stuff. But when you get to word problems, remember, you're going to have to say, there's a lot here. Brain, summarize it. Why? Well, be selfish. You don't want to be writing all day your directions and problems without even doing answers yet. You want to make it short and sweet, but also you're helping your brain say, important. What do I need to use? Good in so many ways. Okay, second big thing. I was going to say bless you, but that doesn't really apply. Domain. Second big thing. Let me get examples up here as you guys are writing. A lot of different examples I could have done for that one, but that works. Let me do a secondary example real fast for the given. I didn't for honors. They have notes similar to you sometimes, most of the time. But I think you guys might need to see. There can be given ones with, or given examples that also are equations. Something like, yeah. There. Okay. Domains, set of all possible x values for a function. I have a little trick to remembering, but tomorrow when we talk about range, I'll bring in my trick from Algebra 1 as to how to remember domain goes with x and range goes with y. But first of all, let's check out the examples. So domains, sometimes it's just given to you. Sometimes they're like, life's too hard, I'm just going to tell you what it is. You might not think they're telling you what it is, but in this one, they're giving you 4 different points and only 4 points. And if domain are all the x's, I show it just with a quick little d colon. Range, I do r colon, just a quick way of noting it. I think last year Mr. Che did some sort of set builder notation the book was teaching you, like all values x such that x is equal to. You can make it snazzy like that. That's okay. It's not bad. But the idea is domain, tell what x's are allowed. Or tell what x's are not allowed and everything else is okay. So what x's are allowed in the first example, guys? Okay, at least the ones that are given, so which ones were given? Because x's are always the first coordinates, right? Okay, and I'm actually going to take Joe's comment and I'm going to improve on it, because not at least, only. Because they didn't say you're allowed to have any more points. So the relation is 4 points, that's it, done. Drop the pencil, walk out the door. Okay? That's it. There are no other points. So you can't say something like x greater than or equal to -1. You can't say that, because what about 2 and 3? And it's not in there. What about 4.79828? It's not in there either. So you can't use an inequality. Sometimes we have to say this, done. That's the domain. That's it. But what about in the second example? What's the domain? Yeah, they gave it to me. You could put it in the snazzy notation and have brace x such that x is greater than or equal to 0. I kind of shorten it just making sure we get the main point. But it's going to be all those x's. 1.1, yeah. 2.79828, sure. 99.743226, ... Yeah, sure, why not? Anything, everything, infinitely many. Greater than or equal to 0. Why? They told me, and I said, okay, fine. But what would be the domain down here? Implied. Ooh, implied's always dangerous, except in math that it's a very specific answer. You don't have to worry about something being implied. You might be right, you might be wrong. Inferring it incorrectly. In math, it's straightforward. There's one right answer as far as the implied domain of this function. And what is it? Square root of y is a thing called an inverse. So it's a thing, just not this thing. A few all numbers. It doesn't give us specific, that's true, but we're just about to look at a picture where it's like, you know what, even though or when, even if, it doesn't give you specific. There are ones where, for instance, y equals some sort of square root of u. And I can just put an x if you want. We have issues with this one. Or when we have y equals like an f of x, a numerator over a denominator, we have issues with that one. Or even though it's not in this section yet, because the book expects us to cover it later, but if we have some sort of log, some sort of base, we have issues with that guy. So just because it doesn't say comma such that, we have issues sometimes. Problems do arise. Why weren't there any problems with him? You guys know x squared, right? He's a parabola. And not only does he go up forever, but he also goes out forever. It just takes forever because it's really, really steep. But think of it this way. What x's are allowed? 1, sure. 10, sure. -1, sure. 0, sure. -17, sure. Positive 1,264, sure. Are any x's not going to be able to be squared? No. So there are a couple of different ways of thinking about it. One way is to think about the graph and say forever left to forever right. I'm going to write that up here really quickly with domain. How left to how right. If you ever are thinking about a graph, you can think about how left to how right. How far left is it allowed to go? How far right is it allowed to go? The air turned on, but now it's loud. How left to how right. And this guy goes forever left, forever right, so all real numbers are totally good. But maybe some of you guys have also seen that really cool shortcut notation for all real numbers. You could use that also. It's like a paragraph sign, but not backwards and with an R. You can use that symbol also. So, what if I was to give you something like this guy without that? What would you guys say? All real numbers. It's a line. It's a line. The line's going to go forever left, like it's going to keep on going that way, and it's going to keep on going that way, right? So what's going on here? And why is this? Oops, nope, too far. And why is this something I have to review in every math class, always, all the time? Pre-Calc, Calc AB, Calc BC. These are the highest maths at our school. Why do I have to keep on reminding? People make mistakes or they just forget. They forget to watch out for, or they don't like the word domain. Like, ugh, that's hard. No, it's not. You just have to remember. Which maybe some of you need to memorize and put it on. Maybe even color code it. Some of your brains do so much better when you have colors attached to ideas. I had a friend in high school. She was amazing, could memorize better than anyone else, but she had to attach colors to her studying. Otherwise, she couldn't memorize a thing. She memorized like whole books of the Bible, but it was all by color coding. It's crazy. Some of your brains need colors. Some of your brains need flashcards. Some of your brains need lots and lots and lots and lots and lots of problems correctly. Then it's just drilled into and you're fine. So here's what I want you to realize. There are 3 different problems, at least for right now. We're going to add to this list a little bit. Like we're going to do logarithm. We're not really doing him now. But I'm showing you him because you saw him last year. We're going to bring in tangent and cotangent and secant and cosecant. They have domain problems too. We're going to add to this list, but for right now, the main two you need are 1 and 2, but go ahead and write down 1, 2, and 3. And what I need you to realize is every time you have to think about domain, when you have an even-powered root. Does anybody have any idea what I mean by that? What? Yeah, so what root wouldn't fall under this? Example? Cubed root. What's the cubed root of negative 8? Careful. Negative 2. Negative 2 times negative 2 is a positive 4, times a negative 2 is a negative 8. Can you get negatives when cubing? Yeah. How about if it was the 5th power? Yeah. 7th power, sure. 9th power, sure. Odds are fine. What's not fine? Because a negative times a negative is a... An even times, a negative times a negative times a negative times a negative. Positive and positive and positive. Anytime you have an even powered, a 4th root, a 6th root, an 8th root, a 10th root, all of those, you cannot have whatever is underneath. Whatever is underneath. I don't care what else is outside. Whatever is underneath, you can't have being negative. This is also called the radicand, technically, if you want a snazzy name for it. But the argument, whatever is underneath, can't be negative, because if I have a square root of a negative number, you guys remember what those numbers are? Imaginary. So I must have my argument greater than or equal to 0. Whenever I see an even-powered root, I can bank on it. I can promise you. Look underneath the radical. What's the radicand? Set it greater than or equal to 0. Booyah. Solve it. You're done. Domain. No problem. What if we have denominators? What's the problem on denominators, guys? Yeah. Well, what can't be 0? So if this is kind of confusing to you, I'm going to say g of x, but you can also, well, let me make it easier. Denominator can't be equal to 0. Now, I'm going to write something real quick because, oh no, we're solving for zeros. Bless you. When we're solving for zeros, we always have to remember to factor, whether we're doing intercepts or whether we're doing domain problems, if we're setting equal to 0. Or finding zeros, we always have to think factoring. That's just a quick little reminder. But we always, for domain, will take the bottom and say, you're not allowed to be 0. Okay, cool. Solve it. You're done. And logarithms, so close and yet so different. Logarithms have these things called vertical asymptotes. We'll see it when we get there. Vertical asymptotes, you're allowed to get closer, but never touching. So therefore, its argument is allowed to be or has to be greater than 0, but it can't or equal to because of that vertical asymptote. It can't equal it. So it's super similar to roots, except roots are going to hit at 0. Square root of 0 is 0. No stress. So many kids get confused on that. Square root of 0 is 0. No problem. Logarithms, nah, there's a vertical asymptote. It can't actually hit. So we're going to do some examples of domain. I think we're going to be able to get them in before we have to leave. But first, if you guys have any sort of color pen, highlighter, something or others about important stuff, this is a super important page because I'm going to reference domain problems for different reasons over and over and over again this year. And it's not always these 3 that I'm talking about, but I'm bringing your attention back to, remember, functions, just because of who they are and how they behave and what they do, sometimes have problems. Ooh, there's a life lesson in that. Sometimes they have problems. But as we get to know our functions better and as we study these things, we'll be able to deal with those problems and try to avoid them. Ooh, life lesson in that one too. Get to know people better, figure out what their weaknesses are. And if you're being a true friend, you won't try to go push all their buttons and have fun with making them mad, hopefully. You'll try to help them in their weaknesses and encourage them in that. Find their problems. Not find them like you're over there looking and judging their life. Not like that. If you see something, be like, okay, can I help you? Not have to struggle with this again. Anyway. But we're trying to get used to these functions to the point, and this is one step, is memorizing. Some of you actually need to, as I said, write it down, memorize it, but hopefully as we practice, you'll just get more and more used to it, more and more used to these guys and what to look out for. So let's look at these examples. If you guys, how's our eyesight? Can we still see it? A little bit bigger? Okay. Yeah, I can make them a little bit bigger. Is that better? We have 4 examples. We're supposed to be finding the domain of each and every one. They're very different. But right away, I think the hardest one is C. Because he's one of those weird geometry-ish, wait, what am I supposed to do? Ones. So let's talk about A and B and D. You can skip lines in between if you're writing them down. Let me give you a second so you can be fully tuned in when we go over them. You guys need to save time, right? What did you write down for the directions? Find domain. Perfect. Exactly what I would have done. How are you writing down the problems? Just got to write it, right? And as you're writing it, you're making sure that you're seeing each of the points correctly. We're going to start with A and B and D. As you guys are writing A, what should your brain be thinking back to? Yeah, the example, the given domain. Matthew, what would the domain be for letter A? Got it. Just steal the x values. All we have are these ones, these 5 points. They're x's, and we're done. Easy. Kind of so easy, it's hard. Our brains aren't used to just like stealing x's and being done. But letter B. Does he have problems? Good. So pause. Everyone look at the page before. Some of you are like, I know what to do. Perfect. Shh, quietly do it. Some of you are like, look at the page before. Find the case with denominators and look to the clue as to what to do. So who's my denominator? Got it. What are we supposed to do to that? Factor if necessary, but oh, he's kind of already good, right? But set him. Good. And what is the 0? Subtract the 5 on the other side, and guess what? You're done. You could write it with snazzy set builder notation, or just say x can't be -5, aka x can be anything. All real numbers except -5. Letter D, does he have problems? Which case? 1. Because he has a root. It's a square root, right, since there's a 2. So what do? We take the, who's the radicand? Who's the argument? And what do we do to that? No. Greater than or equal to. Then wouldn't we have to do a little bit of like algebraic moving around stuff, right? What's something we have to remember with inequalities? When you multiply or divide. So the subtraction wasn't the problem. This is the problem. Good. Positive 4/3, right? So the -4 wasn't the problem. The dividing by the -3 was. So x less than or equal to 4/3. And sadly, we're right here at the end of class, and we have the weird, nasty geometry one left. Do you guys know who's the domain? What variable, V or R? R. Good. What does R stand for in geometry? Radius. Cool. What can a radius of an actual real live figure not be? Oh, so I wouldn't know here. This would be all real numbers. It's not a problem. Pause. Radius can't be negative. What else can't radius be? Yeah. If radius was 0, where's your sphere? You don't have a sphere. So therefore, this one, just understood, implied, R has to be greater than or equal to 0. Okay, so I fail. I'm going to write R greater than or equal to 0. You guys are free to go, though. I'm just trying to finish this last example, but you guys are good. Start homework. See you later. But finish those calculator corrections. There we go.